Hello, everybody. I'd like to go over some of the analysis for our Introduction to Laboratory Measurements lab. One of the first questions you're going to come across is, in the table above, you calculated the densities of a series of objects, all made of the same material, and calculated the average value, standard deviation, etc., based on the calculations. Answer the following questions. Is the coefficient of variation, CV, for the measured density less than 1%? Is this a measurement of your technique's accuracy or of its precision? Select the statement that best answers these questions. So from our calculations previous, we calculated our CV value. The question of whether or not that value is less than or greater than 1% is pretty self-explanatory. But the real question here is this a measurement of precision or accuracy? If we think about what exactly this CV value is, it is the tendency, a rough estimate of how much our points are going to deviate from our average value. It's a span, if you will. So as our measurements become more precise, okay, they all gather around a central tendency, our CV value is going to go down. However, as the points become more randomized around this central tendency, this CV value is going to get larger and larger. The moral of this story is that CV is a measure of precision. For part B of this question, we have, is the percent error for the measured density less than 1%? Is this a measurement of your technique's accuracy or of its precision? Select the statement that best answers these questions. So again, we calculated our percent error before, and the question of whether or not this is greater than or less than 1% is pretty trivial. You guys can decide that. But the question is, what is this a measurement of? So if we think about just the numerator of our percent error calculation, what this is it's going to be the difference, the distance between our average value, the central tendency of all of our measurements, to the true value that it should have been. So if accuracy is how close we got these two values to one another, then our percent error is going to be a value that's going to tell us about our accuracy. As the percent error goes up, this distance gets to be greater and we are less accurate. As the percent error goes down, this distance decreases and we are more and more accurate. Part D of this question is probably the trickiest one out of all of them. Let's read through it here. In many methods that employ multiple measurements, one particular type of measurement may be the weak link that limits the overall precision. For the density measurements you made here, you will determine what contributes most to the CV of your calculated density. The measurements of mass or of dimensions. Typical standard deviation for length and mass using the equipment employed in this lab are the following. So we have two standard deviation values here. The one for the equipment that we used to measure the dimensions is 0.01 centimeters. The one used for measuring the mass is 0.002 grams. Select the data for your lightest object, focusing on its mass and its shortest dimension, and answer the following two questions. Okay, so you're going to pick out an object, the lightest one, and what we're going to do, this is why this is a little confusing, Typically, when we were doing CV, we put in an average value here. But this time, we only have one data point. That one data point is the one for the lightest object. Okay, so we're going to put the mass for the lightest object in here. And then we're going to take the standard deviation for the mass up here. We're going to plug it in right there. We'll multiply that by 100%, and that will be the CV value that we're looking at. We're going to do the same thing down here, only we're going to have the shortest single dimension. Again, we're given a diameter and a height, so we're going to pick the shortest one for our lightest object. We're going to put the standard deviation from above here, and we're going to place in that dimension right here and multiply that by 100%. The question that we would ask ourselves about this is, why would we be focusing in on these? Why the shortest dimension and the lightest mass? And the reason being, if we're given that the standard deviation is the same and dependent upon what equipment we use, the larger the measurement we make with that, the lower the CV is going to be. So what I'm saying is that if we lock in our standard deviation as a certain value because we used a certain technique for measuring it, the larger our denominator is here, the smaller this overall ratio is going to be, and the lower we're going to get our CV value. So therefore, the smallest object is going to make the denominator smaller, okay, which is going to raise the value of this whole ratio and lead to the largest CV value out of the set. So we want to see, is that CV value for that one object much, much larger than the overall CV value for the whole data set? With that in mind, the next question is pretty simple to answer. Which type of measurements, mass or dimensions, had the greatest impact on the CV of the measured density? Choose the explanation. So what we're going to do is we're going to decide which CV value that we just calculated was larger. And then we're going to say this will have the greatest impact on CV. And then we'll choose which of these corresponds to our results. For our next section, we have, in this lab, you determined the volume of water delivered using a mechanical pipette set to deliver 4.00 milliliters. You could have carried out the same procedure delivering 4 milliliter portions of water using a small graduated cylinder. A typical result for such a measurement is the following results of 5 replicate measurements. So this is the average we would have gotten using the graduated cylinder, and here's the standard deviation we could have saw. Calculate the percent error for the graduated cylinder method described above, assuming the intended volume was 4 milliliters. Again, we're using our same percent error calculation. Shouldn't be too difficult there. And in the next section, we're going to calculate the CV for the graduated cylinder. Again, using our same CV calculation here. Don't forget, as I did, to multiply this by 100%. And just as a little hint, I will tell you that for this portion, this 4 milliliter information here is superfluous. It actually doesn't play into the solution. Given what we already know, this one is not too difficult. We're just going to be trying to decide which is more accurate and why. And as we now know, the one with the lowest percent error is going to be the more accurate technique. Again, similar line of questioning, only now we're going to be asked about precision. And as we saw before, the one with the lower CV is going to be the most precise. Moving on to part E, we're asked to decide exactly how we should write these values to show the level of precision that we have with our calculations. So is this 4 milliliters 4 milliliters? Is it 4.0? Is it 4.00? Is it 4.000? So on and so forth. How many zeros do we get to add to this number to show the correct number of significant figures? This is probably best described looking at this table that comes from the PDF that went along with this experiment. Here we can see that if we go to the largest value in our standard deviation, that's where we should be rounding our values to. So in this case, it's the hundredths position, and we round the value to 900. Okay. Here we have the 10 hundredths thousandths position, and you can see that this value is rounded to that thousandths position. Again, here 10 hundredths thousandths 10 thousandths position, and we get an extra significant digit. So you'll want to go back and take a look at the standard deviation for both the graduated cylinder and the pipette, and then decide where you should be placing the zeros in order. In our final question, we are going to be looking at the claims of a manufacturer of pipettes, and we're going to decide whether or not our absolute error was less than or greater than the value they said it should have been, and whether or not our standard deviation is less than or greater to their suggested value there, and then we will choose which of the choices A, B, or C, or D reflects our results.